Exercise 5.3.5. First one, we're going to do substitution. And this is going to be for, since the derivative of t to the fourth is t cubed, 3t cubed, or 4t cubed, the t cubed will cancel, so I'm going to let u be that stuff inside there, equal t to the fourth minus 4, so du would equal 4t cubed dt, and dividing by that we get dt can be replaced with du over 4t cubed. So this problem becomes the integral of t to the third u to the second, and dt is du over 4t to the third. The t to the thirds cancel. The 4 in the denominator comes out as 1/4 integral of u squared du, which is 1/4 integral of u squared is 1/3 u to the 3 plus c, so it is 1/12, and u was t to the fourth minus 4, and that'll be to the third plus c. Number 2. So if we let u be x to the 6th, then the du will be 6x to the 5, and it'll come out and cancel that x to the 5th. So I'm going to write u equals x to the 6th. Du would be 6x to the 5th dx. Solving for dx, for the replacement, it'll be du over 6x to the 5th. So if we're trying to find the capital, the antiderivative of 7x to the 5th sine x to the 6th dx, that's what capital F of x will equal. So it'll be the integral of 7x to the 5th sine u, because u was x to the 6th, and dx is du over 6x to the 5th. Dx to the 5th cancel, so I do have everything in use. The 7/6 pulls out of the integral, and I have the integral of sine u du, and the derivative of what is sine? Well, the derivative of cosine is negative sine, so it's going to be negative cosine of u, which is negative 7/6 cosine of, and I let u be x to the 6th plus c. And now let's do 3. And I'm going to do this one a couple of ways. I'll do it the easy way first. So I could let u be ln(z), or I could let u be ln(z) to the 8th power, as it is. So if I let u be ln(z), du would be 1 over z dz, and solving for dz, I would get z du. Have to multiply both sides by z. So this problem would become the integral of u to the 8th over z, and dz is z du, and the z's cancel. The integral of u to the 8th is 1/9 u to the 9th, using the power rule, adding 1 and divide by the new power, plus c, so that becomes 1/9 u ln to the 9th. I could have written it in here where they kind of wrote the 8 in, plus c. Now the harder way, if I had let u be this, then du would equal, see, I would have to take 8 down of ln to the 1 less power, that's the derivative power rule, times the derivative of the inside, and the derivative of ln is 1 over z dz. So if I were to solve for dz, I would get all this stuff would end up under du, 8 ln to the 7th power, and this 1 over z would become times z. So this original problem would turn into the integral, I let u be that whole numerator, so it'd be u over z, and then I would replace dz with z du over 8 ln to the 7th. All right. Now I have a z still in it, but I think I can solve for ln in this. To solve for ln I'd have to get rid of the 8th power, which means take it to the 1/8, this side and this side. 1/8 power is like the 8th root. So I'm taking the 8th root of u, or u to the 1/8, and that's the way I'll use it, equals ln. So now I got to put that in for the ln. So I get these z's cancel, so I get the integral of u over, and I got an 8 down here that I could pull out, and then I have ln which is u to the 1/8 to the 7th. Okay, so now I have, let's see, this would be u to the 7 times 1/8, which is 7/8 in the denominator, so it'd come to the numerator to be a positive, or negative, so it'd be the integral of u times u to the negative 7/8. So I have u to the 1 times u to the negative 7/8. And so you'd add the powers. 1 plus a negative 7/8 is u to the 1/8, which is starting to look all right. We can do that. That would be 1/8 u to 1 more than 1/8, which should be 9/8, and I'd have to divide by 9/8 or multiply by 8/9. The 8's here cancel, so I get 1/9 u to the 9/8 plus c. But u in this case was um, ln z to the 8th power, so I'd have 1/9 now, ln z to the 9/8 power, or to the 8th power, to the 9/8 power plus c. And I got a power to power, you multiply them, the 8's cancel, and I get 1/9 ln z to the 9th power plus c, which is the same answer I had up there. This was much messier, but still worked. Number 4. Okay. So I could let u be e to the 5x, but I think I'm going to let it be that whole denominator because I dislike having sums in the denominator. So I'm going to call it the integral of, let's start off with what u will be. It will be 1 plus e to the 5x, and so du would be, derivative of 1 is gone, and derivative of e to the 5x is e to the 5x times the derivative of 5x, which is 5, dx. Solving for dx, I get dx equals du over 5e to the 5x. That's in the denominator. That's going to cancel that in the numerator. I called that u, so I get e to the 5x. I could call that u minus 1, but I don't need to. And 1 plus e to the 5x is this, so I get u. And dx that I'm replacing is du over 5e to the 5x. And e to the 5x's cancel. I have a 5 in the denominator, so that becomes 1/5 integral of 1 over u du, which is 1/5 ln u, an absolute value, plus c, which will be 1/5 ln absolute value of 1 plus e to the 5x plus c. And I could actually drop the absolute value because e to the 5x will be something that's always positive, and if I add 1 to it, it still stays positive, so the absolute value are unimportant in this, and that would be my answer. Okay. Now let's do this one. Now, this one, there's a couple of things I could let u be, and we'll do them both ways. I'll start with a simple one. I could let u be simply the 4 square root of y. Now, I got a square root of y in the denominator, but square roots reproduce into the numerator. You shall see here, if I take the derivative of this, that'll be du, and I'm going to think of this as 4y to the negative 1/2. So the derivative would be negative 1/2 times 4, which would be negative 2y. Excuse me, this is 4 to the plus 1/2. So it's 2, 1/2 times 4, 2y to the negative 1/2, getting ahead of myself, dy. So the 2 would go under the du, but this y to the negative 1/2, which means it's y to the plus 1/2 down here, which goes to the negative. It goes to up here when we multiply both sides by 1/2, y to the 1/2 dy. So this problem becomes the integral, the antiderivative, the area under the curve, of 2e to the u over square root of y, and dy is y to the 1/2, which is square root of y, du over 2. The 2's cancel. That's y to the 1/2. That's y 1/2. These two cancel. And I've got the integral of e to the u du. Now the variables match, so it's just the integral. It just turns out to be e to the u. And putting the power back in, we get e to the 4 square root of y plus c. Now, let's do it a little bit differently. Let's say, instead of letting u be just the square root, let's say it was e to that 4 square root of y. So if I let u equal e to the 4 square root of y, du would equal, and I'll have to do some chain rule stuff, the derivative of e to something is e to the same something times the derivative of the inside. And the derivative of 4 square root of y, we found out, was 2y to the negative 1/2. Because this is y to the 1/2. So dy. So when I solve for dy, I'm going to get, this is a positive exponent, so I'll move it to the denominator. So I'm going to get du divided by e to the 4 square root of y. That 2's positive, so it'll stay in the numerator, or it'll go to the denominator, excuse me, when I solve, I have to divide by it. And this y to the negative 1/2 is y to the plus 1/2 in the denominator, so it goes to the numerator over here, y to the 1/2. So my original integral becomes, there's a 2, there's what I called u, over the square root of y, that's all of this, and then the dy is not very nice, it's y to the 1/2 over 2 e to the 4 square root of y dy, or du, excuse me, du. So that's the square root of y, that's the square root of y, they cancel. That's u, and that is also u. That's what we let u be, so they cancel. And the 2's cancel, so I'm left with the integral of 1 du. And if I integrate a constant, it just becomes 1 times u plus c, which means it would be 1 times e to the 4 square root of y plus c, which is what we had doing it the other way. So this one was a little easier to do the derivative, and the integral wasn't bad. This one, the derivative was harder, but the integral was an easier integral, and then we got that. Okay, that was 5. Now let's do 6. All right, on 6, I think I'm going to let u be the sine of q, because the derivative sign is cosine, and it would end up in the denominator of the du, so it would cancel that one, and so I think we'd be done. But I'm going to be changing, this is a definite integral, so I have to watch out for my limits. So if I let u equal sine of q, du will equal cosine of q, because I'm taking the derivative, not the antiderivative, so it's positive cosine, dq. And so my integral becomes the integral of e to the u cosine q, and my dq will become du over cosine q. So they cancel. So I just got the integral of e to the u du. But now I'm in the u world. What would the limits be? Well, if q was pi, sine of pi is 0. So this limit would change to 0 in the u world. And sine of pi over 2 is 1. So this limit would be 1. So the integral of e to the u du is just e to the u, and not plus c now, because it's a definite integral. I'm going to go from 1 to 0. So putting in 0, e to the 0 is 1, minus, putting in 1, I get e to the 1. Okay? Now, I could have, instead of finding out my new limits, I could have stayed with the old limits and changed this back into there. So, say, I don't know those. I don't want to figure them out. But I'll go back to what this was, and it was e to the u, which is sine of q. Now I'm back in q world, and I can use the old limits. Pi over 2. So if I put pi in here, sine of pi is 0, so I get e to the 0, which is 1, minus, and then pi over 2, sine of pi over 2 is 1, and I get e to the 1. So I could have gone back, stayed in the u world and figured out the definite integral, or I could have gone back to the q world and figured it out. Okay, now let's do 7. 7. Basically, they want us to integrate tangent. So, integral of tangent x dx. Now, the way to do that is to go to an alternative for tangent, which is sine x over cosine x. Now, one choice will make that really easy. A different choice will make this one pretty nasty. If you let u be cosine x, the derivative will make a sign and a negative sign, and it'll end up under du, which will cancel the sign, which would be nice. Okay, so du would equal negative sine x dx, and that goes underneath, so I get du over negative sine x equals dx. And so when I make the substitutions, I'm going to leave the sign in. I'm going to put u for the cosine, and for the dx, I'm going to use du over negative sine x. So the signs cancel. Great, I don't have any x's left. I get a minus, comes out, and I've got 1 over u du, which is minus ln of u, or minus ln of u is cosine x. That's a valid answer. Another valid answer is, if we remember our log powers, if we got a number that's in front, like this -1, we can go up as a power, which becomes ln of, let's see, -1 cosine to the -1. It's not the inverse cosine, but the cosine to the -1 power, which means 1 over cosine. But 1 over cosine is secant. So this is probably the way most texts show it, but you could also do that for the antiderivative of tangent. Now let's do it the harder way. And you don't have to watch this if you don't want to. So what if I let u be the sine of x in this? So u equals sine x, du would be cosine x dx. So I'd have du over cosine x equals dx. So this integral, the antiderivative of sine x over cosine x, would become u over cosine x times dx, which is du over cosine x. And we don't have just u's, but this is cosine squared. Cosine squared of x is equal to, if you remember your identities, is equal to 1 minus sine squared. So we get u over 1 minus sine squared x. Well, I haven't got rid of the x, but sine x is u, so this becomes the integral of u over 1 minus u squared. Okay, now that looks like we didn't get very far, but we actually are doing okay here. But I'm going to do a second substitution. So I need a new variable for the, instead of u, so I'll go to the next one in the alphabet. I'm going to let v be the 1 minus u squared. Again, I don't like addition or subtraction in the denominator. So dv would equal negative 2u du. And this is going to be nice because it's going to produce a u in the denominator, which is going to cancel that. So I'm going to get dv over negative 2u equals du. So this problem becomes the integral of u over v. Du becomes dv over minus 2u. The u's cancel. The minus 2 in the denominator comes out as minus 1/2. The integral of 1 over v dv, which is minus 1/2 ln the absolute value of v plus c, which is minus 1/2 ln of v was 1 minus u squared, but u was, in this case, sine of x, so this becomes minus 1/2 ln of 1 minus sine squared x plus c. And now I'm back in the x world. is a legitimate answer, but can we get it to match one of these? Let's find out. See, 1 minus sine squared is cosine squared of x. And the number that's times the log can go up as a power, so I got ln of cosine squared x to the minus 1/2. Well, the 2's would cancel, so I got ln of cosine to the minus 1, which is what this one is if I put the minus 1 up, or I could have left the negative here and just brought up the half, and it would have been ln of cosine with a minus. But cosine to the minus 1, and the 2's are gone, so it would also be ln of secant of x, absolute value, plus c. So we got the same answers. Okay. Now, that was just part A. Now, you didn't have to do it the long, hard way. You could have done it some other way. But now let's look at part B. Similarly, evaluate the integral of cotangent. So I'll do that one. The integral of cotangent would be cosine x over sine x. And since I could let u be cosine x or sine x, that will produce the opposite function, the other function, in the denominator. So I want it to cancel cosine, so I'm going to let the u be sine x. du is cosine x dx. So dx is du over cosine x. So this becomes the integral of cosine x over u, and the dx becomes du over cosine x. Cosines cancel. Integral of 1 over u is ln u, which is going to be ln of sine x plus c. So that's the integral of cotangent. Okay. Let's go over here. Now let's do C. Consider this one. And it says, let u be this. So they tell you what the u to be. So du would equal, derivative of secant is secant x tangent x. And the derivative of tangent is secant squared x dx. So dx would equal du over all of that. And notice that that's going to cancel that numerator. So this integral is going to be that over u and times du over what cancels that. So in those parentheses is that whole numerator, that whole denominator. So the integral of 1 over u is ln u, and u was secant x plus tangent x plus c. Now, another thing to notice is if I factored a secant out of this, I would have a secant plus tangent, which would cancel that. So this is just the integral of, if I simplify that, is the integral of secant x dx. So the integral of secant is this. So in another text, they tell you if you want to integrate this, you have to multiply, but not very obvious, values of secant plus tangent in the numerator and denominator. Get this, and then let u be that, and you can find the antiderivative of secant of x. Okay? So that's not an obvious thing, but that's how you get to that one. And then they say, so we've got that work to figure that one out. Now they say, let's do cosecant. Well, the not so obvious thing to multiply on this one is to multiply by the equivalence, or the similar stuff, which would be cosecant times cosecant x plus cotangent x in the numerator and denominator. So we get cosecant squared x plus cotangent x times cosecant over cosecant x plus cotangent x. So I just multiplied inside by that over itself. So then you're going to let u equal that denominator and du is going to equal the derivative of cosecant x is negative cosecant x minus cotangent x cosecant x times cotangent x. That's what was wrong. And then the derivative of cotangent is minus cosecant squared x dx. And you'll notice that this is the same as the numerator here, only it's the negative. So when I solve for dx, I get du over the negative of what's in the numerator. So when I make my substitution, I get the integral of that gets canceled with that, only for a minus, so I get minus 1 over, and that was my u. And then that becomes minus ln of absolute value of u, which is cosecant x plus cotangent x plus c. Okay. All right. We're finally to number 8. And I'm going to do this one a couple ways. They say, at first glance, it might not work to say, let u be x minus 1, because then you just get du equals dx, and we're not canceling that x. So how do we handle this? Well, this integral becomes x square root of u, and dx becomes du. They're the same. So we still have the x. But if we solve for x in here, x would equal, add 1 to both sides, u plus 1. And so we get the integral of, for x, we're going to do u plus 1 times, for the square root of u, we're going to do u to the 1/2. And then we're going to distribute, and we get the integral of u to the 1 times u to the 1/2 is u to the 3/2 plus u to the 1/2 du. We can integrate that. That becomes, add 1 to this, we get 5/2, so we get 2/5 u to the 5/2 plus, add 1 to 1/2, we get 3/2, so we get uh, 2/3 u to the 3/2 plus c, which is 2/5 u to the 5/2 plus 2/3 u to the 3/2. Okay? Now let's do this one again, but this time let's see, I'll do it over here. Let's let u equal the square root of x minus 1, which is the same as u to, x minus 1 to the 1/2. So du would equal 1/2 x minus 1 to the minus 1/2 dx. So dx would equal, this 1/2 becomes 2 times du, and this to the minus 1/2 goes in the denominator of this side as the square root of x minus 1, which comes up here to be the x minus 1, or x minus 1 quantity, the 1/2. So back to our integral, the antiderivative. We're going to replace the square root with u. We have an x. And the dx we're going to replace with 2 times the square root of x minus 1, which is u, du. Well, we have this x still in this. So we have to go to here and solve for x. So this is to the 1/2. So I multiply, or take both sides to the 2. So I'm going to get u squared, and then I'm going to add 1. So I'm going to get u squared plus 1 is x. Just solving for x in this. So this becomes the integral x, which is u squared plus 1, times 2, which I can put outside, times u squared du. And this becomes 2 antiderivative integral of u to the 4th plus u squared du, which is 2, raise that by 1, 5 and 1/5, so 1/5 u to the 5th plus 1/3 u to the 3rd plus c, and I'll multiply the 2 in, so I get 2/5 u, which was the square root of x minus 1, or x minus 1 to the 1/2 to the 5th plus 2 times 1/3, 2/3 u, which is x minus 1 to the 1/2 to the 3. And I think if you look at that, you'll say that is the same as this. 2/5 x minus 1, and you would cut a power to power and multiply them, so it'd be 5/2 plus 2/3 x minus 1 to the 1/2 times 3 is 3/2 plus c. Okay, so they said convert the integral to, basically they say do all of that, what I just did. So then they say in part D, do this one and do that one. Okay, I'm going to do this one the easier way, not putting the square root on this for the u substitution. I'm going to let u equal x minus 1, so du equals dx, and this becomes x squared, and then this is square root of u, and du x becomes du, but I got to replace x squared, so I would have to add 1, and then that would be what x is. X is u plus 1. But I have to do x squared, so I have to square that. So this integral becomes the integral of u plus 1 squared, x squared, times the square root of u, which is u to the 1/2, and multiplying out u plus 1 times u plus 1, I get u squared plus 2u plus 1. So this becomes the integral of u squared plus 2u plus 1 times u to the 1/2 du. And distributing the u to the 1/2, I get the integral of, see, I would have to add 2 1/2. So that's u to the 5/2 plus 2. U to the 1 plus 1/2 is u to the 3/2 plus u to the 1/2 du. And now I can do the antiderivative. So I'd have to add 1 to 5/2, which is u to the 7/2 times 2/7, plus 1 to this would be u to the 5/2 times 2/5, and I had a 2 already, plus this would go from 1/2 to 3/2, u to the 3/2 times 2/3 plus c, and then I'll put in x minus 1 in for the u's. So this becomes 2/7 x minus 1 to the 7/2 plus 4/5 x minus 1 to the 5/2 plus 2/3 x minus 1 to the 3/2 plus c. And finally, this one. Now this was quite a bit of work. This one is really easy. And that's because it's x squared instead of just x. And when I take the derivative, I'm going to get an x in the denominator, which is going to cancel that x and make it easy. So they give you this one just to show you that they're not all going to be this, where you have to solve for the x. In this case, we got the integral of, slide it up here, of x times the square root of x squared minus 1 dx. So in this one, I'm going to let u equal the x squared minus 1. Du is going to be 2x dx. So dx is going to be du over 2x. And so I get the integral. I got the x. I got the square root of u. So I'm going to write that as u to the 1/2. And then the dx is du over 2x. The x's cancel. And I've got 1/2 integral of u to the 1/2 du. So I add a half to this, or add 1 to 1/2, and I get 3/2. So I got a 1/2 times 2/3 u to the 3/2 plus c. 2's cancel, and I get 1/3 u, which is x squared minus 1 to the 3/2 plus c. And if you wanted to do anything with this, like this could be called 1 and 1/2, which should be 1/3 times x squared minus 1 times the square root of x squared minus 1. There's the half, and there's it to the 1. You could write it in that form also. And that finishes that. No, wait a minute. Number 9. We got more to do here. Boy, we're having so much fun. Number 9. This one shows you another method that you can use to solve these things. For instance, sine to the third. You might think of that as sine squared x times sine x. That's sine of x to the third. But then you can go to the integral of sine squared is 1 minus cosine squared x. And then you can say, oh, let's let u equal cosine x. So du would be, the derivative of cosine is negative sine x dx. So the dx is going to be a du over a negative sine x, and that will cancel that sign, and so we're going to get the integral of 1 minus u squared sine x du over negative sine x. The signs cancel. The negative comes out. You get negative, or I could put it on here and make it u squared minus 1, but I'll put it on the outside. The integral of 1 minus u squared du. Doing the antiderivative, we get 1 becomes 1u, and this becomes 1 minus 1/3 u to the third. Got a minus on all this, plus c. So we get minus cosine x plus 1/3 cosine cubed x plus c. And that's what they have you go through, and then they say, okay, now do the similar thing for cosine cubed. So that would be the integral of cosine to the third x dx would become the integral of 1 minus sine squared x times cosine x. And so we're going to let u equal the sine of x. So du is cosine x dx, and dx will produce a du over cosine x, and that cosine will cancel that cosine. So we're going to get the integral of 1 minus u squared du over cosine x, canceling the cosine x. And so we got this, which is the same thing as we had before, and so we get this except for the negative. So we get u minus 1/3 u to the 3 plus c, which is sine x minus 1/3 sine cubed x plus c. Okay. Now they say we're going to go to the town of Mathland, Michigan. Residential power consumption base is reflected by this. Okay? This is the rate of energy consumption. So if it's a rate, the area under the curve will give you the total amount of energy consumption, if this is the rate of consumption. So that's what they're going to go for here. So sketch the graph. Okay. Let's just use our calculator to do that. And go to y equals, and we're going to clear what I have, and we're going to put 4 plus sine of 263 x plus 4.7 plus cosine 0.526 x plus 9.4, close parenthesis, graph. And we want to know, this is going to be modeling for 24 hours, so, and it's higher, so I'm going to go to my window and go from 0 to 24 hours. I'll go to 25, and let's go from y equals 0 to higher, let's say 10. Graph. Okay? Where T measures in hours after midnight in a typical day. So a lot of consumption at night, probably for heating, and then it goes, or not much, and then when the heat comes on in the morning and for cooking and lights, and then during the day down because people are not doing so much, and then the evening warming and cooking, and heating up, and then not so much again. So that's the pattern they have here. Okay, sketch carefully, label the graph of this from 0 to 24. So we probably could go trace and find critical places. It looks like it starts at 2. And back here at about 7, it's at 5. 5.1, then it gets down to 4 at 12, and then back up a peak at 17, and a consumption of 5.1 again, and then it goes way down to about 2 at 24, and then it starts back up again. Okay, so those are the points I would use to make the graph. Without calculating its value, explain the meaning of this. Well, if this is the rate of consumption, the integral would reduce the total consumption, the number of megawatts per consumed in 24 hours. Excuse me. Determine the exact amount of energy consumed. So that means I would have to do the integrals. And I can get, while we've got the calculator here, let's get the approximate value by going second, calculate 7 from 0, enter, to 24, enter. And I get that, which is 95.78. megawatts. Okay? So now let's see if we get something close to that when we do the integral of this. So we're going to have the integral of 4 plus sine of this ugly number, 0.263 t plus 4.7 plus cosine of 0.526 t plus 9.4 dt. All right, so these are some, so I could do them as separate integrals. So I can do the integral of 4. Oh, and we're doing this for 24 hours, 0 to 24. So I can do from 0 to 24 of 4 dt, which is going to be just 4t evaluated from 0 to 24, which is going to be 4 times 24, 96 minus 0. So that's what I get from the first piece. The second part, I'm going to let u be 0.263t plus 4.7. So du is going to be 0.263t dt, and so I'm going to solve for dt, and I'm going to have du over 0.263t. Nope, derivative of that's no t in there. No t, that was worrying me. Okay, equals dt. So I'm going to have the integral from something to something, I don't want to figure out what that is, of the sine of u du over 0.263, which is, the integral of sine is negative cosine of u evaluated from over 0.263 evaluated from something to something, but now I'm going to change it back to 0 to 24 limits by changing the u back to what that was. So it's going to be negative cosine of 0.263t plus 4.7 evaluated from 0 to 24. So I got to do, I'll figure out the answer without the negative and then put in the negative. So I'm going to put in the 24. So let's just do it this way. I'm going to go down to y2 and going to put in cosine. Actually, I'll just put in the negative right there. Negative cosine 0.263x plus 4.7, close parenthesis. And then I'm going to go to table set and put it on ask. And I'm going to go to table. And I want to put in 0 and 24. And I want to take the 24 minus the 0. And so that's going to be negative 0.16 minus 0.0124. So second quit. Negative 0.16 minus a negative 0.124, and I get negative 0.1476. So I had, for this, I got 96 minus that, and now I got to do this one. And I hope you see that if I let u be the stuff inside, then the du will be over 0.526 will be dt. And so I'll have the integral of cosine u with unknown limits du over 0.526. So the integral cosine is sine of u over 0.526. Unknown limits, changing it back to 0 to 24 would be the sine of 0.526t plus 9.4 divided by 0.526. Oh shoot. I forgot to divide this by 0.263. So I got to divide this by 0.263. Bring this back before I forget it here. So I got that answer divided by 0.263, which is negative 0.561. So I got 96 minus 0.561, and then I got to work this one out. So now I need to go to here, and I'm going to type in sine of, and I hope I'm in radians, yes. So good. Sine 0.526x. Oop, wrong place. Sine of 0.526x plus 9.4, close parenthesis, and then I'm going to have to remember to divide by this, so let's go to the second table, and there's for 24, which is negative 0.033 plus, and this was plus. So that messes this one up again, so I got to fix that again. You see that one was plus and that was minus, so I got the n was minus, then minus a minus, so that makes that minus that plus, so that was right. That's okay. And now I got to do that minus that positive quantity, which is 0.0248. And that's going to be over 0.526. So that's going to work out to be, put it over here where you can see it. So second quit, I'm going to do negative 0.033 plus or minus 0.0248 divided by 0.526, and I get, if I'm not making too many mistakes here, negative 0.109, and so the total power consumption I get is 96. They said exact values, but these are decimal approximations, so I don't know how we're going to get exact. Can't really do exact other than we could have left it with this and this. But anyway, 96 minus 0.561 minus 0.109, 95.33, and what did we got when we did it on the calculator? We got 95.78. So it appears I made some sort of error here somewhere. Minus. Did I have a minus on this? Yes, I did have the minus of this, and that created, at the end was minus, and the beginning was there. So minus this, minus that. So this should be a minus quantity. And then on this one, when I put the end, I got minus 0.033. And the beginning, I got 2 points, so I have to subtract that. So I'm not sure exactly where I messed up there, but that is the idea on this one. A messy problem. Okay? And then it says, what's the average consumption? Well, if I go back to the calculator, second, calculate the area, 7, under this thing from 0, enter to 24. 0, 24, I get It's doing this whole thing again. And it comes up with 95.78. And that's the total consumption in 24 hours. So if I take that and divide it by 24, I get the average consumption. Okay? Oh, I'm going to try to figure out what I did wrong in my arithmetic here, but that's the idea of this.